In our previous video on assessing the regression coefficient using traditional null hypothesis testing, we used the standard error of the regression coefficient as a way of estimating the variability we would expect to see around the null value for a regression coefficient, which is 0, it's just a flat regression line, if the null hypothesis were true. Now we'll flip it around a bit. Instead of using the standard error of the regression coefficient to estimate the range of values we would see if the null were true, and the regression coefficient, our slope for the line, really is 0, we'll use the standard error of the regression coefficient and the slope from our regression model to estimate the range of values for the true population effect. We'll use a confidence interval to estimate a range of possible slopes that reflect where we think we would see the real population slope or effect if we had godlike powers and somehow knew exactly what that real value was for everyone in the population. Let's first look at the confidence interval formula, and then we'll dig into it a little conceptually. The 95% confidence interval for our regression coefficient is equal to the regression coefficient plus or minus the two-tailed t-score that bounds or contains 95% of the distribution times the standard error. Before plugging in values, let's talk a little bit about that two-tailed t-score that bounds 95% of the distribution. Remember, with a normal curve, we know that 90% of the scores fall between z equals negative 1.64 and z equals positive 1.64, or between 1.64 standard deviations below the mean and 1.64 standard deviations above the mean. We can think of that z of 1.64 as being the bounds for 90% of the distribution, or containing 90% of the distribution. Similarly, we know that 95% of the scores on the normal curve fall between z equals negative 1.96 and z equals positive 1.96, or between 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. And we can think of that z of 1.96 as being the bounds for 95% of the distribution, or containing 95% of the distribution. The same idea applies to the t-distribution, except the specific scores that bound 90% or 95% or 99% or any percent of the distribution depends on the degrees of freedom. Now remember, the degrees of freedom tells us the exact shape of the t-distribution, with the shape of the distribution depending on just how thick those tails were. So, how do confidence intervals work? Well, we know that if we have a random sample, the value of the regression coefficient in our sample will be equal to the population value for that effect on average. In that sense, it's a very narrow, very specific estimate of what we believe the population value for that effect is. Because it's very specific, it's an example of what's known as a point estimate. It's an estimate that is, well, a single point. Well, it's nice that it's very precise, but we know that there's going to be some noise and random error in that estimate. We know that it's probably not the exact value in the population. It's going to be off a bit. But how much? Well, that's what the standard error of the estimate tells us. It's our yardstick for how much variability we expect to see in our regression coefficient from sample to sample to sample. At this point, no pun intended, I think it may actually help to calculate a 95% confidence interval based on some simple hypothetical data, and then use that to explain exactly what it's telling us. So Let's stick with using the number of hours a parent reads to their child each week as a predictor of the child's reading ability. We'll say that B1, our regression coefficient for the slope of the line, was equal to 0.90, and we had a sample size of 30, so with n minus 2 degrees of freedom, that would be 28 degrees of freedom. Using Excel or a stats table, we find that the critical 95% t-score with 28 degrees of freedom is 2.048, and we'll say that our standard error for the regression coefficient is 0.35. Based on this, we can calculate the 95% confidence interval for B1 using the formula B1 plus and minus the 95% critical t-score times the standard error of B1. Plugging in those values, this solves to 0.9 plus and minus 2.048 times 0.35, which is 0.9 plus and minus 0.7168. Okay? Now, 0.9 minus 0.7168 is 0.1832, while 0.9 plus 0.7168 is 1.6168. One form of notation for these values is to write the two numbers separated by a comma in a pair of parentheses so that it's parenthesis 0.1832, comma 1.6168, and parenthesis. Those slopes of 0.1832 and 1.6168 define the bounds of our confidence interval. We can illustrate it here visually with this shaded area that reflects the range of slopes we would expect to see based on our sample if we sampled an infinite number of times. One side of this area corresponds to the slope of 1.6168, and the other corresponds to the slope of 0.1832. So again, this shaded range of slopes reflect our 95% confidence interval. Well, that's nice, but what does it mean? What does it really tell us? Now, you'll hear people talk about having high confidence or 95% confidence that the true effect for the population is somewhere in that range, or that 95% of the time the effect in the population falls somewhere in that range. But let's take a closer look at technically exactly what the 95% confidence interval is telling us. Let's say that I obtain one sample and calculate the 95% confidence interval for a regression coefficient, and it gives me a range reflected in this blue line, with the lower limit to the left and the upper limit to the right. The confidence interval is the entire range of scores along the blue line between these two values. Now, let's not worry about what the actual values are. Just think of this as a range of values for our regression coefficient. Different people then go to the same population and get a different sample and calculate a 95% confidence interval for the regression coefficient in that sample. Notice it's different from the first because it's a different sample. In this case, it's a little narrower and a little more to the lower end of the distribution. We then get another sample and another sample and another, and so on an infinite number of times. Okay? Let's then say that I somehow magically find out exactly what the true value for the effect of that variable is in the population, and indicate it here with this black dashed line. Notice something. See how in most of the samples, the 95% confidence interval that was calculated overlaps or contains the true population effect size. Now, not always. If we did an infinite number of samples, there would be some cases where the 95% confidence interval based on that sample does not overlap or contain the true population effect size. And that leads to a more technical and accurate description of a 95% confidence interval. If you have an infinite number of samples from the same population, and you calculate a 95% confidence interval for each of those samples, 95% of those 95% confidence intervals would contain or overlap the true population value. Again, if we collected an infinite number of samples, 95% of the time, the 95% confidence interval someone calculated based on each of those samples would contain or overlap the true value. But 5% of the time, it would not. 5% of the time, the actual population value would be outside this range. Now, remember, I don't actually know what the true population value is. We don't know what the effect of studying would be if we looked at the entire population. That's why we're estimating it using our sample. But confidence intervals give us a sense or estimate of that range in which we think the actual population value exists. Because of that, we think of the confidence interval as an interval estimate of the effect, which is different but complementary to the point estimate that we see with the regression coefficient itself. That sense of the precision of our estimate can be very informative. For example, the same regression coefficient can either have a very small or a very large confidence interval, depending on the data. A small confidence interval suggests that the value of our coefficient, that point estimate, is measured very precisely. We can feel good about the estimate of that specific value. On the other hand, even a statistically significant effect may have a very large confidence interval. In that case, a statistically significant p-value paired with a large confidence interval tells us that while we may feel comfortable that there is some effect, we really have no idea what the actual size of that effect is. Now, before wrapping up this video, there are two final points that I want to make about confidence intervals. First, while we've focused on the 95% confidence interval, the exact same principles and generic formula can be applied to calculate a confidence interval for any range of confidence. Now, in addition to the 95% confidence interval, you typically may see a 90% confidence interval or a 99% confidence interval. For the 90% confidence interval, all you do is replace the t-score that bounds 95% of the distribution with the t-score that bounds 90% of the distribution. For the 99% confidence interval, all you do is use the t-score that bounds 99% of the distribution. And of course, always base those t-scores on the distribution with the correct degrees of freedom. The second point I want to make before wrapping this up is this. Notice if we look at the t-distribution, we can see that the t-score we use to calculate the 95% confidence interval is also the same t-score that we would need in order to reject the null hypothesis if we were doing null hypothesis testing with an alpha of 0.05. Because they're based on the same t-score and the same standard error of the regression coefficient, there's a synchrony between a 95% confidence interval and an alpha level of 0.05. The ranges they describe are in fact the same size, just centered on different things. It's centered on 0 for null hypothesis testing, and it's centered on the observed value for our regression coefficient when we're calculating a confidence interval. Consequently, if the 95% confidence interval does not overlap 0, like in this example, then the p-value for our regression coefficient will be less than 0.05, and using an alpha level of 0.05, we would reject the null hypothesis. If the confidence interval does not include 0, then we are, for want of a better word, confident that the effect is not 0. we're sufficiently confident that there is some effect. That sounds a lot like rejecting the null to me. Similarly, if the confidence interval does overlap 0, then we're saying that 0, or no effect, is a plausible value. How can you reject the null hypothesis if you're simultaneously saying that no effect is a plausible result? To me, that sounds like you'd want to fail to reject the null hypothesis. Now, I am simplifying things a bit, and there are some subtleties between confidence intervals and hypothesis testing that I'm glossing over here. But I don't want to miss the forest through the trees. It's very valuable to see that parallel nature between a 95% confidence interval and an alpha level of 0.05 in hypothesis testing. They'll ultimately lead you to a similar place and similar conclusions, just in different ways and from a different perspective. But that's also why you generally want your alpha level and confidence intervals to agree. 95% confidence intervals with an alpha of 0.05, and 99% confidence intervals with an alpha of 0.01, and 99.9% confidence intervals with an alpha of 0.001. That way, you don't end up in a situation where your conclusions are inconsistent based on which approach you're reporting. Now, this wraps up our discussion of confidence intervals for regression coefficients. But you'll see the same principle applied to all sorts of confidence intervals for all sorts of different effects. Okay, I hope you found this informative. Bye for now.